All right, so we'll start. So I'm Geoffrey Fox, and I'm at Indiana University, and I'm going to give the first half of the discussion of FutureGrid. And the discussion of FutureGrid starts with an overall discussion of sort of some context about grids and clouds, and then it goes on to discuss the details of FutureGrid. So we will first discuss some general issues. As we saw already from Alex, there are several important trends, including the data deluge, which he gave great details of, and there are obviously many hardware trends, including the multi-core, which he also pointed out with especially the GPU chips, and for the purposes of this lecture, another critical development is the emergence of clouds, which are either replacing or augmenting grids, depending how you want to look at them. Another important trend, which is actually also was discussed by Alex, is the growing number of sensors, of which the most pervasive sensor is a smartphone. And I expect all of these things to continue. I visited Intel recently, and they have a huge amount of research on interfacing sensors to clouds, and those sensors wear nearly all smartphones. And my impression at the moment is that another change from, say, a few years ago is the commercial developments are moving more rapidly than the academic developments. Grids were mainly an academic activity. So I usually show this curve here, the so-called hype curve, which should be actually reissued this year from Gartner in about 3 weeks' time. And this tells you where the various technologies are, and you will notice that if you look near the top, there is a yellow star, and that is cloud computing. It is at the top of the hype curve, and so that doesn't really tell you, except it just says it's well hyped. It doesn't actually say whether it has value or not. My belief is it has huge value, and it will mature and go through the trough of disillusionment, and then move on to the plateau of enlightenment, productivity. They're all roughly the same thing. And you will also notice appearing on this graph, Web 2.0 and service-oriented architecture. So one important lesson from, say, grids is that grids made extensive use of services. Services are not, the importance of services is unchanged. So you can explain clouds in many ways, either operationally by their functionality or by some of the reasons they're becoming important. And one of the major reasons they're being developed is that there are economies of scale of placing a lot of computers in the same place, preferably with sources of power which are relatively cheap and green and things like that. In this graph, which I think I took from Microsoft, this slide, they estimate that the cost of network storage and administration is maybe over a factor of 5 cheaper by placing large numbers of computers in the same place than by the more traditional approach of spreading them across the country. And so you can sort of see one major difference between grids and clouds. Grids are integrating systems across the world. Clouds are consolidating systems in one place. And that's an important difference. This on the right-hand side of this graph, you can see that the cloud data centers are truly enormous, much larger than a football field or whatever unit you want to use. And these cloud centers use substantial power, maybe today 20 megawatts, but they're going to go up to a factor of 10 more than that, and they'll have maybe hundreds of thousands of computers in one place. An interesting feature of this deployment, which is sort of amusing, if not quite so fundamental, is that the unit of computer is now the container. So the model is that you just build a giant data center with a bunch of plugs, and then your truck brings the container of computers in there. You plug your container in, and now you have more computers. This is all to do with making the cost of computing much cheaper. You can remember that Alex pointed out that 20% of all servers are deployed today by the Web 2.0 slash search vendors, Google, Microsoft, Amazon, Yahoo, etc. And so this particular, the importance of clouds is sort of inevitable because such a large number of computers are being deployed to them. If you go and look at typical clouds, the most important commercial cloud at the moment is Amazon, and that will be discussed in a lecture this afternoon. Well, depending on where you are this afternoon. Maybe it's always this afternoon. You will find that if you go to Amazon, we started a few years ago, they originally just allowed you to rent computers and use them. Now they offer a great deal more capabilities, including relational databases, programming models, which we'll go through, like MapReduce, and data and table data structures, and so on. We do not have time in this tutorial to go through all their capabilities. We will just give you an overview of some of them this afternoon. Many of you come from the TeraGrid and high-performance computing community. On July 13th, Amazon announced that they were offering high-performance computing as a service. You can not only get a virtual image, you can get a virtual cluster, and you will find that if you type the obvious things at the search engines. And as an example, they came in they just took a cluster and deployed it at Amazon, and that particular cluster ran Limpack and plopped in as number 146 in the top 500. So it's not at the top, but for the many users who want modest-sized clusters, they are now available from Amazon. To do that, of course, they have to change some of their models, because normally when you get an image from Amazon, it is totally virtualized, and so if you get two images, there's no reason for them to be near each other. To build a cluster, you have to put your machines near each other, work quite hard on the virtualization to ensure the communication is high performance, and so on. But at least Amazon has listened to some of the comments from the high performance computing community, and now has this offering. So remember, this is another interesting feature. This field is changing very rapidly. There's an awful lot of people working for Google, Amazon, and Microsoft who are advancing clouds at a rate that I think is a little faster than maybe in academia. An important feature of clouds is the as-a-service philosophy, and probably the most important service is software as a service. That's actually been around ever since you had service-oriented architectures that says that your software runs and it has some interface. You send messages to that interface and it gives you results. And I think applying systematically software as a service is an important trend which will continue and will make for more robust, easier to deploy systems, because it means that each service is isolated. It is not mixed up as it often is when you use more normal deployment of putting things in /user/bin or however else you deploy software. Deploying it as a service means that it is much more possible to address security and other deployment issues. The original Amazon offering is called Infrastructure as a Service. That means you just get the ability to have a raw virtual machine which you put what you want on it. But as I pointed out, Amazon offers a lot more, as does Azure and Google, and those a lot more are called, by definition, platform as a service. And so platform as a service includes things like HPC clusters, queues, databases, tables, etc. And as I pointed out, everything is a service, and there's meant to be a little picture at the bottom of the slide to illustrate that for the basic cloud. And I've even put in one of the supercomputers there. I forget which one it was, Kraken maybe. And you're meant to sit there at your client, have your credit card available, and do your computing. I have never actually understood why NSF does not use credit cards. I asked Charlie Catlett that many years ago. It just seems to me the obvious way. You'll just have NSF money, funny money, and charge your computing in that fashion. But I guess they don't do that. But anyway, everything then is done as a service, exchanging messages, whether you be a user or your different components of your system. And as Judy taught me, Cyberinfrastructure can be thought of as research as a service. We already mentioned the importance of smartphones. There are sensors as a service. And you could say that almost in any area, what we're trying to offer is wisdom as a service. So that's this picture here. So if you look at the world and look at what Alex described, and what we want to do to make decisions is we have an enormous number of sources of data where we have biological instruments, satellites, say smartphones, LHC colliders, or just something which produces information, webcams, or just computers that spew out data. All those data produce messages which then run through other software packages which themselves run on grids or clouds, and they all go through some so-called workflow which link them together. You come up to a portal which is in the top right-hand corner here, and they transform from data to information to knowledge to wisdom, and then finally you make the decision about what you want to do, and you collect your Nobel Prize or however what else you would like to collect at the end of all this. So all of these things are services, and clouds are then just one way of implementing these different components. I pointed out the developments I noted when I went to Intel, and that is illustrated here with these various small sensors, which again Alex has done a lot of work here. And sensors as a service points out that when at least my Android smartphone, it does everything to the cloud, it's backed up to the cloud, and the clouds are very appropriate for smartphones and sensors, because clouds most easily give you a single virtual image, and certainly a single virtual image can cope very easily with a sensor of at least the size of a current smartphone. And so I expect there to be a growing use of clouds for this world. And then once you've got all your billion smartphones in the cloud, then you're going to be doing things like run MapReduce to aggregate the data from those cell phones and decide who you can sell whatever you're trying to market to those people, whether it be scientific knowledge or jewelry or what have you. So now we come to cyber infrastructure, and here Craig produced this quote, which must come from some magnificent federal document, and he notes it's not terribly easy, which is true. So the purpose of at least the research that we do at PTI, and I think a lot of the audience, is trying to understand how to build cyber infrastructure, and remember, that's research as a service. And we build it in this fashion here, Judy's diagram. Cyber infrastructure at the top, built on software. Software is built on platform, and platform is built on infrastructure. And that's true. That architecture is true whether you use grids or clouds. But with cloud, you just have a particular flavor of all these layers that they're done as a service, dynamically on demand. So here is some discussion on clouds and grids. So we don't really have to debate what a cloud is. I would define a cloud to be whatever Microsoft, Amazon, and Google offer, because they're highly motivated to make money, and they will evolve clouds as they see fit. And you could say that the scientific community should not be subject to the whims of these commercial enterprises. On the other hand, you could say scientific community should try to exploit the huge commercial investment into high quality hardware and high quality software, and that there is no way that NSF and NIH and NASA, etc., and DOE can compete with the software investment necessary to build large-scale systems. I already noted actually that this number here, the clouds are now 4%, growing to 14%. That's actually an underestimate, because I told you 20% of all servers were purchased by cloud companies. So there's 4% and 12%, which are the estimates of the IT expenditure directly going to clouds today. That's in commercial companies outside the internet giants. But this came from IDC. I would certainly expect that to continue. And we have various types of clouds. Public clouds, those are the ones offered by Amazon and Azure. There are some important issues about privacy, which means they're not always applicable. If you're a commercial company with some really important data that you don't want to reveal, or if you're working in the health science field where there's a lot of privacy issues, the use of public clouds is not so obvious. That doesn't mean that you can't use clouds, but you're going to have to use a private cloud, which means you can use the same software and architectures, but you're going to use it on FutureGrid or Magellan or one of the private clouds available, or else you go to your innovative chief information officer at your university and say, this is enough, we're going to switch everything to use cloud technology, and we will stop our current architectures. There are some difficulties here in private clouds, namely the key feature of public clouds is the elasticity. They are so big that if you want 1,000 instances, you can get 1,000 instances. It's not so obvious you can ever build a private cloud with the elasticity that you need. Another problem is if you look at the current academic available software, such as Eucalyptus, Nimbus, and OpenNebula, and now there's OpenStack, to run private clouds, that software is not as capable as the commercial software. It basically mimics what was available 3 years ago from Amazon. As I noted, Amazon has enormous improvements to their software. So that issue as to how we can actually provision a private cloud with the richness that the public clouds have is not so obvious. And so it means if you go to your public cloud, Amazon, and use SimpleDB, which is that table data structure, and then your biology experimentalists love that because it allows them to do Excel in the cloud. You can't do that so obviously on your private cloud, because you then have to go to this open source software HBase, which supports table data structures, and then you find it probably doesn't work very well because not so many people use it. So I would say, as I mentioned, I consider commercial organizations way ahead of the academic activities. All right. Well, we already mentioned services are critical. We will keep services. And as Craig points out, that the hype is not all obviously correct. Namely, it is not. There are certain academics who've stated that TerraGrid is crazy. Everything can be done in clouds. There are others who say clouds are crazy. Everything can be done in TerraGrid. And they note correctly that TerraGrid is cheaper than Amazon, partly because the machines on TerraGrid have various subsidies, because they have been built with a lot of institutional support. So the exact mix between TerraGrid style machines, which you might call MPI engines, versus clouds is by no means obvious. because it's a mixture of technical issues, how you actually provision clouds, costing issues, who pays for what, and etc. And there's also, as Alex mentioned, a lot of difficulties with data, and UPS and FedEx are clearly a very important part of your cloud infrastructure. So I would say one of the things FutureGrid is trying to do is to shed light on these issues here by providing an environment which we'll describe that allows you to do MPI, MapReduce, clouds, what have you, on the same hardware in a reproducible, elegant fashion. So we've more or less said most of these things already. I say grids have taught us a lot, and they have pioneered service models. They developed things like workflow, which are bound to continue. Workflow is still the same critical idea, which is not changed much, but as you go from grids to clouds. However, there are performance issues on grids, and actually the performance issues on grids are probably worse than the performance issues on clouds, because clouds are just virtualized. Those machines are still probably in the same geographical location, whereas grids link machines across the world. So I would suggest that clouds roughly can execute any jobs done by grids, but they have various positives compared to grids, the elastic idea, these platforms available commercially. There are these performance limitations with MPI, which Amazon is trying to address. I don't think Amazon is expecting to run a petaflop MPI job, so they will only be addressing the low end of clusters. And whether they're really as cost effective as other approaches is not quite obvious. There's a big debate in the listservs which monitor this area. And my guess is that we're going to have a world which obviously will have MPI engines, grids to manage data, because data is intrinsically distributed. If you remember, I asked questions of Alex Saleh about this issue. And we'll have clouds running a lot of jobs which are more effective in that model. So we need all of this stuff. I will not, in this slide, talk about MapReduce. It will be discussed by in many of the talks we have today, because MapReduce is a very important programming model. If you like, it's the MPI of clouds. It's actually quite similar to MPI in many ways, and it's a higher level than MPI. It does automatic parallelization, but it does not support some of the operations MPI does. And so there are these two implementations which we will hear about, Hadoop and Dryad. Hadoop runs on Linux and Java. Dryad is a Windows HPCS solution, and I believe that just as people in this field used to learn MPI, they should now all learn MapReduce, and we will try to teach that to you. And I will not discuss this. So one critical feature which actually is relevant for, say, people working on exascale is that MapReduce is much more fault tolerant than MPI, but that's also that fault tolerance, it comes with some of the limitations of the applications it can do. And one of the important research issues is this trade-off between fault tolerance and performance. And that's actually also true at the very highest end for just MPI engines. How you build an exascale supercomputer when everything is failing at some reasonably often is not quite so obvious. So I believe that MapReduce has enhanced the set of research on these issues of fault tolerance. So if you want to read about this, you can just go to Amazon. O'Reilly has many books on this field. The one I've read in detail, the Azure, the Windows Azure, which is the O'Reilly Azure book, is extremely good. But I have not read the other ones in detail. But I am sure that there are many of these books are good. If you want to learn more, please don't forget to submit a paper to our CloudCon conference, which is in sunny Indianapolis in in the beginning of December, and we will also have 4 days of tutorials if you want to follow up on this, and the deadline for papers is August 20th. And so for the final part of this section, I wanted to remind you why we're going to cover clouds and MapReduce today and tomorrow. Clouds were developed to process internet data, and say 20% of computers are sold to the internet data vendors. And we heard about astronomy, and we will hear on Thursday about other applications, but information retrieval is the largest data-intensive application, and clouds and MapReduce were developed to solve that very large application. And if you look at the web, which I did last night, MapReduce processes 20 petabytes of data at Google in 2008. I assume it's gone up. Or maybe they have a secret technology which replaces MapReduce, which is now being used. And poor old LHC, which is some high point of scientific research, is only going to produce 15 petabytes of data a year. And so this, and Alex pointed out that if you have more than 100 terabytes, you're in some trouble if you're an academic person. So we're riding the coattails of this enormous commercial development. And the other sort of more technical point is, if you look at the structure of data analysis programs, whether it be in biology or particle physics or information retrieval, which is a scientific data analysis field, you will find that many of the algorithms, not all of them, favor loosely coupled cloud-like architectures, and you do not need the strict synchronization and corresponding constraints on the system that is true of MPI engines. And so finally we get to FutureGrid after we've just told you why it's useful. And FutureGrid is meant to, as I said, to allow you to explore these different approaches. So this is now with FutureGrid. And so that was FutureGrid 100. Now I have the first part of FutureGrid 101. And I try to motivate why it is very important to look at new applications, because we're living in a time of computing when things are rapidly changing. I started computing when paper tape was the latest way to do things, and was replacing punching individual holes in cards, and then we had key punches and all sorts of other exciting revolutions. But the rate of change of technology is as rapid today as it was many years ago. And FutureGrid is essentially a engine which allows you to request essentially any secure environment, and it will be dynamically instantiated, and so you can explore clouds, HPC, Linux, Windows, etc. And we had our first users in June of this year, so that's just a few weeks ago. And we hope that by the end of September we will be more ready for broad use. This current class series, the largest use we've had so far, uses most of our available nodes, and FutureGrid will become formally part of TerraGrid and allocatable by the TerraGrid process around September 2000 or October 2011. FutureGrid has lots of wonderful partners. It's led by Indiana University. We have Purdue, San Diego, Chicago, Florida, University of Southern California, Tennessee, Texas, Virginia, Dresden in Germany, and some of these are software or benchmarking partners. Others have hardware, and that hardware must be shown here. So the compute hardware is listed here, and what's notable about it is how little hardware there is. This is not your petascale Blue Waters machine. This is a carefully selected, modest number of nodes arranged over the country with a reasonable sample of important architectures, because we're not trying, FutureGrid is not trying to run production to do great science. FutureGrid is trying to provide a highly flexible architectural environment to develop the middleware, networking protocols, and the applications that will enable great science to be done on production machines that are much larger than the FutureGrid system. I think FutureGrid's around be 5% of, maybe it's probably even less, probably a couple of percent of the total size of TeraGrid. I think TeraGrid must be some 200,000 cores, and FutureGrid is about 5,000 cores. We have at the moment Cray as the one specialized machine. We will get a new specialized machine, which we haven't decided what it is because NSF has just added a whole bunch of machines to their network. Exactly which one we'll mimic, we're not certain. So we have, but our workhorse machines are IBM and Dell clusters, which we can dynamically configure. We have some variety of storage. You heard about the data capacitor yesterday from Justin Miller. And we have at Chicago, San Diego, and Texas a bunch of storage devoted to this system. Notice, these are not petabytes of storage. These are still quite modest. Networking is sort of interesting. We have a variety of networking. Most of them are actually high performance networking, so these are not the typical networking you'd get on clouds. That's because we want to be able to run on most of our machines MPI, so you can compare Hadoop versus MPI and make realistic, correct judgments on which is the most appropriate. We have some interesting features of the networking, such as a network fault and delay generator. That might be. And we have also a dedicated network. We have a dedicated network which links all the sites except Texas, and that allows us to isolate experiments as necessary. You may note that Indiana runs Internet 2 and National Lambda Rail, and so we're able to have a high capability in that area. We have the obvious links to other networks, including to the European, to Europe, where there's a well-known project called Grid 5000, which you could say that is the nearest project internationally which matches FutureGrid, and you could say they pioneered this idea of being able to do experiments in this fashion. And we have a good collaboration with them. And you will notice that most of our systems are operational except the Dell system at Texas, whose purchase was delayed. And it is now installed and running tests, and we expect it to become part of FutureGrid in a few weeks. We run Inca to monitor it, and so if you go to the FutureGrid website, you can find out whether the systems are operational or not. And here's their operational status displayed on a Google Maps. And this points out that we have all these sites linked. Everything except Texas has this isolated network. There is a FutureGrid router, I think it's in Chicago, and it has this impairment simulator which allows you to inject the delays into your messages, faults into your messages, so you can mimic various interesting circumstances which are hard to do directly. And the Texas machine just is connected to us via the TeraGrid network. It is possible that will change because the costing of the network to Texas, which made it prohibitive to link them initially to our private network, is meant to be changing. This is this impairment device, and actually I would like to see a few more applications to use this. We have the University of Delaware, which has a very strong networking research group, has a proposal to look at this, but it has a very flexible interface allowing you to specify some highly customized changes to the packets, say the delay and the artificial loss. So I've already sort of said this. It is FutureGrid is supporting research. We're not doing production. We're developing the research and research software which will allow production on Amazon, on TerraGrid, on your local systems using the modern technologies, and we're allowing you to compare very rigorously the different approaches. And although I started off discussing clouds because they are the most recent, we support grids, clouds, MPI in a very solid fashion. So sometimes NSF really puts out press releases saying we're a cloud. We are actually a simulation engine which can simulate clouds but also can simulate anything else. And our success will be measured by how successful we are in generating new science from the people who write new software on FutureGrid and they go and run it in production and make science. So I'll let you browse this slide on the Google Groups website. This is just a list of some of the early uses. We're still looking for good early users, so if any of you are inspired to make a proposal, there is on the front page of the FutureGrid website a form you can fill in to apply for time. And so you can look. We have even we have an industry application which is running CFD codes, and we would also like to see more more network, more industry, but also core, cloud, grid, MPI, and also just applications, people who want to change a particular field. Another important area that we have, we support is education, and in fact you could say that's what you're going to be using FutureGrid today and later this week is an example of FutureGrid for education. So FutureGrid does research and education, which are the missions of NSF. Here's a slide which you'll see later on. They've done it, discussed in more detail to show the sorts of things you can do. This is looking at a particular bioinformatics code, CAP3, and this particular study done by the SALSA group is looking at the comparing Amazon, Azure, FutureGrid running Hadoop, and FutureGrid running Dryad, and is looking at the performance in various fashions comparing these approaches. And so the advantage of FutureGrid is you can run Windows, you can run Linux and Hadoop on the same machines and get some comparisons that have some stability, and as Azure changes you can keep coming back to FutureGrid and check how that performance changes. So this is providing some uniform environment. So as I pointed out, we're very interested in supporting new education. So if you have your faculty member who wants to develop a new computer science course which involves destroying the operating system and things like that, or developing using clouds of various types, then FutureGrid may be a place that faculty member could develop that course. Okay. So if we look at the software architecture, so this is not the software that FutureGrid will support the development of, but the software that runs FutureGrid. It has to do various things. It has to allow us to configure the resources in a dynamical fashion. It has to manage it in a way that if you run an experiment, you can effectively reproduce that experiment. And eventually it has to be run at TerraGrid production quality. Now, one feature of FutureGrid is that we like software as a service. So we will try to provide, where possible, various software environments that can be customized by the user and used. And we have already commitments to support several important pieces of software so that you can request images implementing this software, including the TerraGrid stack, Condor, Point, G-Lite, Unicore, Genesis. These are all traditional grid environments, and of course MapReduce and some of these cloud platforms such as Bigtable, which is what you see with Azure Table or Amazon SimpleDB. So we're very interested in getting users of FutureGrid who find a piece of software that we don't have and say, we want to bring up that software on FutureGrid. After our work, we will have presumably done some research. We will continue to support this software so other people can use it. So if you have that desire, we'll be very pleased to hear from you. So here we have the different components of the FutureGrid software. Some of it is standard and available on all systems, like portals and monitoring. But we have image repository and the ability to generate images. That's sort of traditional cloud-like software, standard cloud-like environment. We have inter-cloud networking software from the University of Virginia, performance from Tennessee and SDSC. A critical part of our software is the software that schedules and deploys images. That's called RAIN, for Runtime Adaptable Insertion Service. And that should allow you to be able to make requests like this of FutureGrid, that I want to get just 30 infrastructure as a service Zen images. And then you may even prefer KVM. Or you may want a slightly more sophisticated environment, Eucalyptus or Nimbus. Or you may want MPI running on Windows or Linux. And or you may at a higher level want, as we did a demonstration, running this well-known bioinformatics program BLAST between FutureGrid and Grid 5000. So these are typical types of requests that you would make of FutureGrid. And so this slide here illustrates this in a picture of how and this is probably the most unique feature of FutureGrid. Unlike clouds, have a virtual machine sort of core, and you load things onto virtual machines. FutureGrid loads things onto bare metal, including virtual machine software, hypervisors. So that's a key difference, that we're dynamically reconfiguring from the bare metal up, not from the virtual machine up, the hypervisor up. Now, something we're developing, because whenever I give this talk, people ask me, what about root access? And what about this, attack on the software? So we have to be highly sensitive about security. And I pointed out a critical feature of using as a service. As a service allows a much more robust deployment, because you just interact with some software with messages, and you can do much less damage that way than you can if that software is installed in /user/bin. I want to point out, so this is almost trivial, but it's worth noticing. If you go to Amazon, you can get S3, which is storage as a service, or you can get Elastic Block Store, which is storage attached as a disk to your machine. So this issue between as a service versus installing in your own image is an important issue. And to know when you want one and when you want the other is an area I think it's not so obvious what the answer is, and more research is needed, because as a service is undoubtedly an easier way to do things than putting it on your image, just for a trivial combinatorial reason. If you have n features and you allow you to put each of those n features on /user/bin, you have 2 to the n possible images. If I only allow you to access those features as a service, I only have n possible services. So the management of as a service is orders of magnitude more effective than the /user/bin approach. So we will have this suite of vetted images, and you're using vetted images in your tutorials today. These will typically not allow root access, and you as FutureGrid users can create images, and you can request that those images be vetted to allow them to be used later on. And as I said, we're pretty interested in people who are going to create generally useful images. And if you want an image which allows root access and does dangerous things, we have to think quite carefully, and we'll probably have to put it on a virtual machine, and we may even have to use the fact we have an isolatable network to isolate you so you cannot do too much damage. And I will not go through this slide. The image creation process, it shows at least thought about the issue and how you create an appropriate image, how you customize it, and how you deploy it, and how we update it to make certain it keeps up to date with patches and things like that. So this is not maybe fundamental research, but it's very important. As far as I know, it is not the type of thing that's necessarily done on other systems. Just as a final example before I hand over to Craig, I'll just point out some work done by Judy's group, which first demonstrated this. This was dynamic virtual clusters. We demonstrated this at SC09, running on some of the very earliest FutureGrid hardware. So you have here an iDataplex with 32 nodes. On top of that, XCAT is the software that deploys on demand on the bare metal. It's controlled now by Moab, but at that time it wasn't, I don't think. And in this case here, we deployed either Linux on virtual machines, Windows, and Linux bare metal. And we then showed some demonstration of this being done dynamically. And that's shown on the last slide, which unless you have your lights off, you can't see. That's a well-known feature of the presentations. They're wonderful on your laptop, but sometimes don't have the right color for your display. But the main point is of this this experiment which we ran at SC09 is it told you some timing. But when you wanted to fix the operating system and change the applications, that took 30 seconds. When you wanted to reboot the whole system from scratch into a totally new environment, that took 5 to 7 minutes. So this fact that it's a few minutes, which we continue to see, is why we believe that it is perfectly realistic to say that we will boot your system on demand on bare metal. We will either reuse an image if it is already running, but if it isn't already running, we will take this few minutes to reboot your system. So that's the end of this part of the talk, and the next part is done by Craig, and he will describe more operationally how you use FutureGrid. But we could have some questions now, maybe, if you have any general questions about clouds and grids, etc.
Please give me the question.
All right.
I'm looking at your benchmark one sequence assembly in the cloud, slide 33.
Yes.
Yeah. For some reason, it's good, but Hadoop bare metal efficiency seems to be less than Azure. Is that because Azure is doing a better job? But when I look at the right slide, Hadoop bare metal takes less time than Azure.
Yeah, but you see the absolute times, unfortunately, have to be thought of carefully. Namely, our measurements of Dryad versus Hadoop on FutureGrid are on the same hardware. When I run on Azure or I run on Amazon, we have no idea what hardware we're using. So you have to look I would suggest that given the early stages of our study and the early stages of this infrastructure, we shouldn't take 20% differences too seriously, because there are many deployment issues and hardware differences that can give you that type of change. So I conclude from those graphs that these approaches are comparable, and I didn't go into the deductions from this. We would claim the performance of these various approaches is similar. The MapReduce based approaches using Dryad or Hadoop have some advantages because the parallelism is a little more automatic, and so they're somewhat easier for the user to deploy. But this was not meant to allow you detailed comparisons between these systems, because they are actually quite similar.
Okay, I have one more request. is there any webpage in your SALSA site where you explain how you build the cloud images and all those things so that we don't have to reinvent because you guys put a lot of effort on that?
Well, Thelina will go through in his Amazon talk this afternoon. He will actually do the CAP3 example. And you can welcome to send the SALSA group email and they will try to help you. But the TAs here are all from the at Indiana are all from the SALSA group. So just send email to the appropriate Google group mailing list.
Thanks.
Any more questions, or shall I hand over to Craig? All right, we'll hand over to Craig.